Hello, distinguished guests, professors, and judges. My name is Shaivi Bhatt, and along with me I have Hubert Argasinski. For our fourth-year design project, we created an e-textile-enabled glove to be used in virtual reality applications. Before we begin, I would like to introduce you to the team. Hubert is our software lead on the project. He has worked as a software developer at companies including ClearPath Robotics and Hubert. Brandon is responsible for prototype implementation. He has completed 2 co-op terms at Teledyne Delsa as a new product engineering specialist. Ramsey is our electrical lead. He was responsible for conducting circuit simulations and soldering. I was responsible for material deposition since I have previously done research in a lab setting. We chose Dr. Irene Goldthorpe and Dr. Marwa Abdullah as our consultants due to their expertise in nanowire device fabrication. Let me start by giving you some background information about our application. Virtual reality is a simulation of real-life situations. It is typically done by images and sound through an external headset. VR is mostly used for entertainment purposes, such as gaming, movies, and television. However, it can also be applied to simulated learning environments, such as new pilots and drivers. Some common headset brands include Google Cardboard, Samsung Gear VR, and Oculus Rift. The current VR market is over $7 billion, and that number is expected to double by 2020. From the graph on the right, you can see that over 86% of the market is dominated by lower-end VR headsets, such as the Samsung Gear VR and Google Daydream. It is estimated that over 12 million of these lower-end devices were sold last year alone. So you may be thinking, how are these VR headsets actually controlled? Currently, the device is controlled by a panel located on the side of the headset or through external remote controllers. The panel on the side of the headset is uncomfortable for the user since their arm might get sore from holding it up too long. The panel is also impossible to see since the user's eyes would be covered with the headset. Remote controllers are also available. However, they are bulky, expensive, and they're difficult to find while the user is wearing the headset. Thus, both the panel and the remote controllers take away from the VR experience. And we aim to solve this problem using nanotechnology. From the problem definition, we were able to identify a set of customer requirements. We identified that the customer will be looking for the following things in a good controller. Reliability, meaning that the controller responds when it is clicked and it responds accurately. The controller should be compatible with a variety of smartphones. It should also be lightweight, inexpensive, aesthetic, durable, safe, comfortable, and easy to use. By taking into account the customer requirements and the problem at hand, we were able to come up with the following solution. We deposited nanowires to a cotton glove to create a VR controller. It has 4 detectable inputs along with the thumb, which is used to select. The number of inputs is the same as the panel on the headset and can be used for commands such as left, right, up, and down. The fingertips are responsive to the touch of a bare thumb. It is Bluetooth compatible as well as lightweight, inexpensive, easy to use, and comfortable. It is also entirely safe since there are no exposed nanowires, no unbound nanomaterials, and a very low current is used. I will now pass it on to Hubert to discuss the theory.
Thank you. So the first major design decision we made in the design of our glove is the use of capacitive touch sensing. It consists of an electrode covered by a dielectric and a non-conductive material such as the user's finger approaches the sensor. A capacitor is formed and a microcontroller can detect the time it takes for the capacitor to charge, and once the charging time surpasses a certain threshold, it can interpret that as a signal to send to respond to. The other major component is the trace, which connects the microcontroller to the capacitor. We decided to use a silver nanowire e-textile for our trace and electrode, and the EVA polymer from the deposition process is used as the dielectric for the capacitor. So moving on, we decided to implement our design with a simple RC circuit. Shown on the left is a 1 input, which essentially corresponds to 1 finger or 1 sensor, and then we decided to scale this up using to 4 inputs correspond to 4 fingers. We decided to use a 1 mega ohm resistor in our circuit. This was recommended by Arduino, and our tests confirmed that this is the optimal resistance value to use in terms of sensitivity to response time. So moving on to our silver nanowires used for traces and the electrode. We decide to use a transprinting process as this results in a mesh. Ideally, our material would be conductive, transparent, low cost, and safe. The transparency is for aesthetic reasons. Silver is conductive metal, so it satisfies the primary requirement of being conductive for the material. The mesh helps us satisfy other three requirements. Due to a mesh, as shown in the SCM image, there is space between the conductive paths in the electrode. This allows light to pass through, allowing the material to be transparent. It also uses less silver nanowires compared to other coating methods such as dip coating or brush coating, as those create continuous film. Due to the areas between the conductive paths, less nanowires are used, resulting in lower cost for our product. Also, due to the transprinting process, as shown in the picture, there is a polymer coating which adheres the silver nanowires onto the fabric. This means that the user is never actually in direct contact with silver nanowires, meaning that the final product is safe for use. So on to the deposition process. What is transprinting? We begin by pipetting a certain concentration of nanowires onto the transfer paper, and my rod is used to uniformly spread the solution over the surface of the transfer paper. The my rod helps align the nanowires to increase the probability of conductive pathway. This is then repeated X amount of times for the number of layers required to increase the number of nanowires on the transfer paper to increase the conductivity. The transfer paper with the nanowire solution on top of it is then annealed for 1 hour at 100 degrees Celsius in a vacuum oven. This helps reduce the resistance between nanowire junctions by fusing them, and it can optionally pass through a rolling press afterwards to further press the junctions together, helping them fuse. Afterwards, the transfer paper with the silver nanowires is placed nanowire side down on the fabric and placed into a heat press at medium pressure for 30 seconds at 190 degrees centigrade, with a press sometimes 30 seconds, and which transfers the nanowires onto the fabric. The EVA polymer passes through the mesh and sticks to the fabric, and then some is left on top to coat to keep the nanowires in place. After 10 seconds after removing the fabric or transfer paper from the heat press, it is peeled. This step actually causes a lot of problems for us, as if the stress applied is too high, the nanowire mesh will break, or if the stress is too low, transfer paper bits will be left over, ruining the aesthetic of the trace on the electrode. We found our rolling motion during the peeling helps find the optimal balance at the cost of a slightly increased resistivity. The rolling motion induces a stress which degrades portions of the mesh, but it results in the most reproducible results, and hence why we chose to stick with it. Moving on to the final component of our design is the software. We use Arduino, as this is industry standard for programming microcontrollers. An Arduino program consists of two components, the libraries, which are essentially reusable modules, and the sketch, which dictates how the libraries interact on the board. We built upon two standard libraries, the Capsense, which is used to detect input from a capacitive touch sensor, and Bluefruit, which is Adafruit, the manufacturer of board's library for for sensing of sending Bluetooth signals to a Bluetooth receiver. This means that the circuit can interact with any Bluetooth Low Energy enabled device. We added a custom library that integrates the two. It has a glove manager class that dictates how the Capsense and Bluefruit that manages the communication between the Bluefruit and Capsense. There's a base finger class that is used for reading inputs from that use the Capsense library to read inputs from the sensors, and then dictates how the finger responds. There are three events that the library responds to: the user pressing on the sensor, the user holding the finger down on the sensor, and the user then releasing the finger from the sensor. The sketch extends the base finger through a polymorphistic approach to code the response of each individual finger, so each finger can send a different signal to the target device. So some of the trade-offs that we considered in our design is conductance and transparency. The sparser the mesh of silver nanowires, the more light can pass through, and hence the more transparent it is, but the less nanowires for the less conductive pathways for the current to travel through. And the opposite is true. The denser the mesh, the closer posters and continuous film, the higher the conductance, but less light can pass through it, resulting in a less transparent film. We also consider cost versus features. For instance, we could add an accelerometer to increase the functionality of the glove, allowing the user a richer experience, but those components cost money. As we are targeting the lower-end VR market, we decided to provide the user with the minimal feature set required to perform the tasks in order to reduce costs, allowing the glove to be more accessible. Finally, as aforementioned, we consider response time versus sensitivity. As the resistance in the circuit increases, the capacitor charge, it takes longer for the capacitor to charge, resulting in a longer response time, but a better signal-to-noise ratio, and no false positives. And it also allows us to detect inputs from further away, so the user does not necessarily have to touch the circuit for us to be able to detect the input. If we use low resistance, the circuit responds faster to a press, but the noise ratio is worse, and we require an absolute touch as opposed to just close proximity. We decided to go with 1 mega ohm resistor, as this gave us the best trade-off between sensitivity and response time. So moving on to our implementation, we began with a simulation of an RC circuit to see how the different parameters affect the operation of the circuit. We use AutoCAD and PSpice for this. By changing the capacitance which corresponds to the finger approaching the sensor, we are able to see how the response time changes and how the resistivity affects it. And once again, results show that 1 mega ohm resistor is optimal. After this, we implemented the model we simulated on a breadboard and iterated on it to arrive at our final prototype. Sorry. We were able to first use the e-textile electrode shown in the second prototype to ensure that our theory works and that it is able to act as a capacitive sensor. We moved that circuit onto a glove to see how the capacitance of the human hand affects it, and how moving the components affects the baseline and the readings we receive. We then moved on to multiple inputs to ensure we could differentiate between different signals, and we finally integrated that onto a glove and our final prototype. We had to add a grounding wire, as when the circuit became wireless and used a battery, the capacitor had issues discharging. So we added a grounding wire that connects to the user's hand to allow the capacitors to properly discharge. The major challenge we faced in our design was the peeling step of the deposition process. As shown in the pictures, there was a lot of transparency being left over on the samples. This resulted in a very low yield rate of approximately 5% usable samples at a sample size of 50. We tried adjusting many parameters such as the heat press temperature, the concentration, the pressure, the annealing time, until we finally realized that using a different transpaper resulted in much better transferring, and we were able to bump our yield rate up to 77%. And we also optimized the layers and the concentration so nanowires used to give the most transparent peel versus conductivity. Shown on the slide is our final prototype, and as shown in the video, it can be used to interact with a device such as a Bluetooth device such as a phone. We made the traces longer to keep all the wires hidden. We needed copper tape to be able to access the silver nanowire underneath the EV layer. We added a pocket to hold the microcontroller and hide all the exposed circuitry. The final parameters used to achieve transparency is 10 milligrams per milliliter of silver nanowires and IPA with 2 coatings. This also helped make our deposition smoother and the peeling better. We added, as I mentioned, a grounding wire to allow the capacitors to discharge. We added a cotton glove inside the user wears below this glove to stabilize our baseline. And we end up using 1 mega ohm resistors. As aforementioned, this gives the best best sensitivity response time. And we added small 100 ohm resistors to protect the circuit board from electrostatic discharge. Shaivi will now talk about the results of our final prototype.
As you can see from the results above, the RC time constant is much higher from the baseline. Figure 1 shows that a RC time constant of 1000 is achieved by just tapping the electrode once, and the following fingers are also visible from there. We completed 3 different kinds of mechanical testing to determine the durability of our glove. The test allowed us to see the simulated different kinds of stresses in real life. We tested 20 samples to see the change. The top graph shows that there was minimal change in resistance under bending. The middle graph shows that the results of a double bend test, and the bottom graph shows once a sample was rolled around a rod. This didn't affect the resistance greatly, but the middle, the double bend affected the resistance the most. It almost 5-fold increase, which may cause future issues. We also tested the lifetime of 11 nanowire samples by measuring the resistance at specified intervals over 1 month. We then created a mean control chart to assess the variability of the resistance of the nanowires over time. From this, we can see that the mean resistance for all the samples except for one has stayed within the limits, and most samples are on the lower end, meaning their resistance did not change much per day. Taking all this data into account, we can now see how the final prototype compares to initial design and customer specifications. We ensured that the device is responsible and reliable by optimizing the resistor values in the circuit. By using a microcontroller with Bluetooth, we ensure that it's compatible with multiple electronic devices. By using a Featherlight microcontroller, along with the silver nanowire e-textiles, we were able to keep the controller very light. We optimized the cost of our controller to be approximately $75, which is very comparable to the $600 of glove controllers today. We were able to hide the electronic components easily to ensure a transparent and aesthetic glove through the use of the silver nanowires. Since there are no exposed wires, no unbound nanomaterials, and a very low current is used, the glove is very safe. Though our glove test withstood the single bend and the roll test quite well, it began to degrade very quickly under the double bend test. And since the user is likely to bend the controller for more bend tests than what we tested, our current controller does not satisfy this requirement. And while our glove is easy to use, the requirement of putting a copper tape under the wrist makes it slightly uncomfortable, so we also said that that's not passing. So completing this project, we learned a lot about silver nanowire technology. We learned that the silver nanowire mesh is ineffective on stretchy materials. It causes the mesh to break. We also learned that mechanical stresses cause the mesh to degrade more quickly than lifetime. Finally, we learned how to take a product from its conception all the way to its final prototype. If we were to continue developing the glove, we would perform further durability tests, such as washability, to see how the gloves would perform under extreme environments. We would complete thorough toxicology studies to ensure this glove is safe for consumers. We would also wish to test our processes on a variety of fabrics to ensure maximum comfort. We would look into reliable deposition methods, since this technique was not 100% reproducible. And we would also learn how to optimize the pattern trace. We would like to acknowledge Dr. Irene Goldthorpe, Dr. Abdullah, and their grad students for all the help and guidance they have given us, as well as Dr. Jen Coggin, Dr. Backhouse, Dr. Barbie, and Dr. Aziz for providing us with insight over the past few years. Thank you, judges, for taking the time out of your days to be with us today.